So welcome to my second talk, perfect hashing in NetBSD. Again, a short overview. I'm going to talk about perfect hash functions, what they are, why you should care about them, some characteristics, a bit about the history of perfect hash functions, some of the mathematical background, two different important algorithms for creating them, the application in NetBSD for that actually uses these algorithms and provides them for applications, the constant database derived from that as well, and a bit as a work in progress, how I would like to use it in the routing code. So what are perfect hash functions? A hash function, most of you should be aware of that, is basically a function that maps some keys to some integers. They can be found in pretty much any programming language to implement associative arrays or dictionaries or however they are called. And they are perfect if they are injective. So different keys are mapped to distinct values. In other words, these are hash functions that don't have collisions. And that's a very, very important property to have, because it makes them deterministic in terms of performance, and you can avoid things like collision attacks on them. And we are talking about a minimal perfect hash function if it maps exactly to the range to the first n numbers, where n is the number of keys. Why should you care as programmer or a system integrator? Well, as I mentioned, there are algorithmic attacks published in recent years that try to force collisions to occur inside hash tables and make you waste time that way. So, for example, Python or Ruby had this attacks published, where you had a web application and you gave it the right arguments. It was very easy to compute the resulting hash table slots, so you could make it do linear searches for a few 10,000 keys every single time and just waste a lot of performance that way. So they do have the very nice property that they have deterministic timing, and they are also very useful because they can be very compact. So you can use them as index data structure even if your key set itself doesn't fit into memory. So if you have a large data set you want to store, Bloom filters are one of the ways to check is a specific key inside my storage, and that needs a very small amount of memory, and with perfect hash tables you can even get a more interesting answer. Well, if it is inside the hash table, you have to look at that position. Well, and of course, many here are computer scientists, so it's nice to do some actual science. And last but not least, we use them in NetBSD, so it's interesting to understand what's going on here.
When you say they're used in NetBSD, do you mean hash functions in general or perfect hash?
Perfect hash functions. There are some important characteristics different perfect hash functions can have. So one interesting property is do they preserve the key order? This basically means I have an ordered set, and the hash function will map to integers in the same order. Or in other words, I can instruct the hash functions which specific mapping I want to have. The second important question is, well, how much space do I need for the hash table description? And what computational cost is associated with it. If it's not a minimum perfect hash function, it's also useful to know how dense it is, because, well, that's additional overhead I have to pay for. A short history. Bostic published the predecessor of GNU-GPerf around 1984 in some news groups. That was the time I was born, so it's quite old. Knut has a few examples for the construction of them in the art of computer programming. Pearson has a very interesting construction mechanism which looks surprisingly like the RC4 string cipher, and all of this have two things in common. If they work, they are very fast, but finding a perfect hash function with these mechanisms doesn't have to work, and it doesn't have to work in a reasonable time frame. So once you are beyond, say, 10 or 20 keywords for a compiler, for example, it's very soon impossible to use GPerf, for example. It just runs and runs and runs and never finishes. So a bit of background, some building blocks for the modern algorithms. There are so-called randomized hash functions, which are basically families of hash functions that contain some parameters, some initial seed. And they're useful to know because they can be used to prevent the mentioned complexity attacks if I keep the seed secret. There are certain families that are so-called independent random hash functions, and that basically means I can use them like random variables from statistics and apply all the knowledge from statistics to them. Once I have random variables, I can use them to construct random graphs. So there's a whole field, for example, part of the Ramsey theory, that looks at properties of such random graphs. One of them that is very interesting for this application is if I have graphs where each edge connects 2 or 3 nodes, and this graph is dense enough, I won't find cycles. And what basically happens is if I have twice as many nodes as edges, I'm very unlikely to find a cycle, and if I have 3 graphs, it's even better. I only need 25% more nodes, and the probability of finding a cycle in the tree is basically 0. I'm going to come back to that in a moment. So the first algorithm I want to look at in detail is called CHM, after the persons that invented it. This one is from 1992, and I think it's the first algorithm that has expected linear runtime. It's expected because we are basically talking about randomized algorithms, so you might have a bad choice of the initial seed, and the construction doesn't work in that case, so you'll just try again, and expected linear runtime in this case says the number of tries you have to do is very, very small. The algorithm creates an order-preserving, yes?
Linear in the number of keys or in the number of bits?
The question is, what is linear of? I'm always talking about linear in the number of keys. So basically, one of the building blocks are the random hash functions, and you do one pass of with a hash function over the key set, and that's from that point on the key size itself no longer matters. So
basically, n is the lower bound for every algorithm which does perfect hashing.
Yes, and actually, it has been proven that you can't be faster than expected linear, of course, and you can't do it without the expected part either. There's no way to build in linear time a perfect hash function. So this specific algorithm gives minimum perfect hash functions that are also order preserving. That makes them very easy to use in applications. And the downside is that the space requirement is relatively large. So basically you need to store an integer for every single key. The key depends on how many keys you have. And the factor C is the number 2 or 1.24 from the earlier slides. The computational cost is basically, if you have a key, you compute the random hash functions, 2 or 3 of them, reduce the values to the key range, do some table lookups, sum that up, and compute another module. How does it look like? So we have 4 keys. We apply our random hash functions, get some values for that, and now we consider this a graph. What I'm showing is, doesn't get better. Okay, sorry. It's basically the values from 0 to 4 and some associated number. And I'm now following paths and assign values so that the sum of the edges is equal to the key number. So I don't have to do anything for key 1. For key 3, which is the next, I'm updating the value associated with node 4 to 3. And I'm repeating that as long as there are some edges that are not assigned. Because this, I do know my graph is cycle-free, I can always find one edge.
Ooh.
that's not completely assigned yet.
Okay.
And one easy way to figure out if the graph is cycle-free is just do that, and if at some point you have an edge where no... Let me think for a moment. If you have an edge you can't process that way, you basically have a cycle, and that's the easiest way to find it out. So the second algorithm is much newer. It's from 2007. It's not order preserving and it's not minimal. It's about the same computational cost, but it's much more compact. So using 3 graphs, you need less than 2 bits of storage per key. And if you apply some counting filter, you can get a minimal perfect hash function using less than 2.8 bit per key. This counting filter would add another 2 table lookups and a population count. There's a price for it, of course. So same example as last time. The only difference is before the sum of the node values was a key number. Now it's basically which of the 2 hash functions does represent the key. So key 0, I'm saying should be represented by the hash function 1. So the sum of 0 and 1 has to be 1. For key 3, basically the same, and so on. It's kind of boring for a small example. It gets more interesting the larger it is. I have to encode, well, one of the digits 0, 1 or 2 for each node. That can be easily encoded into a byte by combining 4 of them. So that gets a pretty dense representation. There is one newer algorithm which is hash display and compress, which is even more compact, but it's also significantly more difficult to implement and also slower on the read side, so I'm going to skip that one. So we have the NetBSD perfect hash function generator. It was incidentally started in 2009 as well, which is the reason, or one of the reasons why CHD is not included. It didn't exist at the time I started with this. There is an existing project to implement the different perfect hashing algorithms, CMPH, but that's under GPL license, and the code has some issues as well, which made it less attractive for NetBSD. So I wrote them from scratch. And there are different options for the generator to choose the algorithm, the density, or stable seeding. Stable seeding is what we use in the build system because we want to have identical results for later ones as well. So how much does it take to actually create hash functions? As test case, I used Webster's unabridged dictionary as shipped by the various BSDs. So the first case is 230,000 keys. the second 76 keys. Easy to see that the runtime scales pretty much linearly in the size, as expected, and the number of retries is also pretty low. It doesn't necessarily correlate with the runtime directly, because if it hits a case where the graph is cyclic, it depends on well, how long it took to hit that time to decide how expensive the retry is. And that's on my laptop, so taking much less than 1 second to compute the perfect hash table for all 230,000 words. That it works very well even on the backs. Just an example of how the hash function would look like. I just removed the constant array because that would be pretty boring and long. So there's basically one function, the machine-independent vector hash, which provides a fast-seeded hash resulting in 3 32-bit integers, and it gives the same result independent of the architecture. Once you have that, we are doing some trivial computations, and that's kind of the magic part. The compiler will actually replace modular operations with 2 multiplications, a bit of shifting. That's also black magic, but compilers are good at doing that. So let's come to the last part of my presentation. We have a lot of places in NetBSD where we are using the Berkeley database as index database, for example, for etc P3B or etc services and so on. There are a number of limitations that are problematic. There are no atomic transactions, and that means all those places have to deal with power failures, and effectively they are doing a copy update moves scheme. So they either recreate the database from scratch or copy it first, and once everything is written to disk, they just rename it over the existing file. PDB has a relatively high database overhead. I'm going to add some numbers to that later. And this is important for embedded systems because it makes it less attractive to ship those databases already prepared. The code of Berkeley DB is very complex. Even if you look only at the hash table code, let's not talk about the implementation of the B tree. It uses per application database caching, so there are multiple copies of the data in the system, and for that very same reason it also needs logging if the program is actually using threads. We do have SQLite in NetBSD, which is nice because it does support transactions. It does have some limitations when it comes to read-only access, because even with a write-ahead log, you need to have write permission to the log file to prevent someone else, from writing. There's still quite a lot of database overhead, and in terms of code size, it's significantly larger than BDB. So I sat down and wrote the NetBSD constant database. It provides, first of all, indexed variable size storage. So basically the equivalent of the rect database from BDB. And second, it provides a perfect hash index into the storage. It doesn't store the keys itself. So the application is responsible for being able to verify that the matched entry is actually what it is interested in. The primary reason for that is many applications have more than one way to look at the data, and they have different means of synthesizing the access keys, and storing the keys would just result in duplicated data. The CDB code is extremely small. It's something like 1.5 kilobyte for the reader and a bit more than 4 kilobyte object code for the writer. It's, I think, at least a factor of 10 even compared to the BDB hash database. And the databases are generally comparable in size to the textual sources. It's log-free and exclusively dependent on memory mapped I/O. Reading needs something like 3 block accesses for the key lookup and another one to get to the data. So it's even for well, normal disks with spinning, it's not that bad. And in NetBSD 6 we are using it for the services database. It's part of our new terminal info implementation and the device database. Not converted yet are the password database, because there are some nasty compact hacks for NIS, which makes it difficult, and the database for the last use of TTYs. It's interesting to see that in pretty much all of those cases that have been converted, the database size is less than 1/4 of what it was with BDB. So that's quite noticeable. And it's also faster to write. So the last part is future work for the route lookup. The basic problem we are facing in the network stack is we want to find the best matching prefix in the routing table, and that's been implemented using a radix tree. The code for that is very complex. Part of that is because it tries to solve a more generic problem than it has to.
Didn't you remove the non-continuous netmask crap?
Not yet.
You should, we did. It was very well worth it.
I know.
Keep doing that, I want that code.
So, and the other problem is the radix tree is basically the kitchen sink of the network stack. Whenever someone needed to do an address-based lookup, they try to fit it into the routing table or just another copy of the radix tree. So
yes, that's the typical approach. Copy the code, do a tiny change, and then let it rot.
Actually, not even copy. Just add another entry in the routing table because we have it, so it's free. And
multiple copies as well, slightly changed.
The problem here is, well, we are going to do an lookup in the radix tree, so we would have to do another lookup for the data otherwise. Well, if you don't have a prefix lookup to do, because what you actually want to look at is a full IP address. Use a hash table. It's definitely faster than doing it inside the radix tree, because adding more levels to the radix tree is not free either. The biggest problem with anything that tries to touch the route lookup is that the radix tree implementation is not only the data structure, it also contains a lot of policy choices. So, for example, the question which is the best prefix contains choices of host routes that don't have a net mask, so they are handled differently from prefix length 32, and you can have multiple prefixes with the same length and data part, which one will it pick, and so on. So all of this is nicely hidden away in this hideous complex radix tree implementation.
It's not very well hidden, unfortunately.
Yes. And well, David Young introduced some very thin wrapper layer to isolate most of the rest of the kernel from the radix tree, which is kind of like 50% of what needs to be done. So what has to happen next is move all the policy decisions out as well. And once that is done, we can actually touch this data structure and look for more efficient implementation. So what can we do with it? One of the alternatives are compressed trees. I'm not going to look into those, but multi-level hashing. So the basic idea is if you want to search for the best matching prefix, you can do this by doing a binary search on the possible prefix length. And if you have many different prefixes, this has a very nice property that it scales logarithmically, not in the number of prefixes, but the size of the prefixes. So for IPv6, for example, that would be the logarithm of 128, which is significantly smaller. The radix tree, for example, scales linearly in the prefix size. So in the worst case, you have to follow 128 levels for IPv6. To be able to do that, you need to add a few markers in places where a longer prefix has to be found. And if you add references to whatever prefix is shorter to those markers, you can avoid all kinds of backtracking. So just let me pick some nice example of a stupid routing table that's not too unrealistic. So we have a default route, we have a loopback network, and we have a number of different local networks here. And for the markers to work, we need to know in which order we want to search prefixes. So let's do the stupid one where we do a strict binary search. So we have to add one marker for 192, 168 with a prefix length 16. And this one would cover the default route, so we keep that as well. We have to add a marker for 10.0 itself, and for 11.8. So let's let's say I want to look for 192.168.05. First, I would do a probe for 192.168 with prefix length 60. I'm finding my marker here. And next, I would do a search for /24, which would give me my actual route, and I'm done. There's a button in the slides. If I want to look for 10098, I would first search for 100 with length 60. I would next search for 1009/24. There's no hit, so I know the memorized 10/8 is my best match, and I'm done. It's very nice to use perfect hashing here because it makes the potentially expensive part, the memory access, deterministic. If I use the BPZ algorithm with TrueGraph and no post filter, I have a 50% utilization, which is okay, and 2-bit storage requirement per key. It makes sense to have separate hash tables for larger prefixes. So, especially for IPv6, I want to be able to use single 64-bit entries for the shorter prefixes and only require larger entries for longer matches. And the nice part is I can easily fit something like 100,000 routes into the level 3 cache of a modern CPU, which would be about the size of the BGP announcements nowadays.
What? No. You're at 400,000.
Doesn't matter. It's just a factor of 4, and with the 2 bits additional storage, it's not that bad. So the critical decision, and that's where I'm really looking forward to do some actual benchmarks, is how much time do I need to construct the perfect hash table, and how often do I need to rebuild it because new prefixes appear.
Well, I can tell you, a BGP router, like 100 a minute.
The update rate of BGP itself is not the problem. The question is how often do you need new prefixes appear or disappear. That's the difference.
Common. It's very common. Some leaf side flapping is very common.
Sure, but I don't always have to remove them. I just have to update it to be the same forward address as what's covered. So it will be interesting to see. The other interesting part to look at is I don't have to do a stupid binary branching. I can actually look at the distribution of the prefix lengths, and doing that correctly can often allow me to do less than 2 lookup probes on average to get the route that's actually of interest for me. So let's summarize it. Modern algorithms are quite fast and practical. They can be used for performance-sensitive read-mostly data. They are also useful for on-disk databases, and you can use them now in NetBSD 6. Questions?
Yeah, I have a question. I want to know if I merge your implementation to FreeBSD, merging cost is easy or hard?
Okay, the question is how difficult is it to port this, for example, to
Yes,
FreeBSD?
yes.
It's pretty straightforward. The NVPath itself is part of the toolchain in NetBSD. So the only parts you need to provide it is the randomized hash functions, and also the population count routine. That's it. So integrating it in another third-party project is trivial. The requirements for the constant database are almost the same, so that's also very easy to integrate.
Thanks.
Other questions? Yes?
Thank you very much for your very interesting talk. I'm especially interested in the hash table for the routing table. So you presented the binary tree.
Yeah.
Yes, but we have, as far as I remember, we have some kind of tree-bit map. Do you know that?
Yes, the alternative, what I mentioned, is a compressed tree,
Yeah.
which is, the idea would be you can, well, you can merge part of the branching of the radix tree, so you always do the check like 4-bit or 8-bit at a time.
8 bits and
Right.
yeah.
So
In case of 3-bit map, they didn't have the pointer to the data structure. So
both are very viable approaches. The compressed trees work very well for IPv4.
yeah.
I don't think they work as well for IPv6 because due to the longer prefixes, you still have more indirections necessary, and the indirections are basically what are hitting the caches very hard. So whenever you actually have an uncached memory access, the performance is going to go down the drain. It's that slow nowadays.
And I have one more question. So in case of the, I'm sorry, I forget the name of the hash name that you presented last week. Yes, right. Sorry, route hash table for the route. Maybe before the summary slide, I think.
Maybe the previous one?
Next one. Oh yes. Does it exclude the backtracking?
That one was basically the generic introduction. For the radix tree, you don't need backtracking. If you want to do the multi-level hashing. Okay, so basically,
Yes.
if you look at the second example,
Yeah.
when I did, I had a hit for 10.0.16.
So passive expansion.
And I'm now doing a search for 10.0.9.
So you needed to another entry in order to exclude the.
Basically, I don't want to have to search again for prefixes shorter than 24. So with a back reference, if I want to avoid that backtracking, I need to store what route is the best match for 10.0.16.
So do you know? Do you have any idea when we apply this approach to the real internet? I mean, like routing table for BGP. So how many this kind of
marker
entry
entries?
can be
entries basically it depend on what's the depth of the search tree. So if you do the static binary search for IPv4, you have at most 5 levels of probing. The logarithms of 32. So at most you have 4 additional markers per route. Most of them will be shared simply because the prefixes are not at the maximum depth, and they share different lengths. So that's okay, but even the overhead, I don't have exact numbers at the moment. I think the experiments were it's much less than 2 in terms of overhead for the larger BGP tables.
Thank you very much. Thank you.
Other questions? Well, in that case,
I have one.
Okay.
So you say it performs well and it's practical. That's on your summary
Yes.
slide. And I don't really doubt it, but I have a question. Are there any like pathological inputs that can cause strange behavior? Like either performance that's slow, or it doesn't ever finish, or uses too much memory, or...
well, it basically depends on the random hash functions you are using. So as long as the random hash function has the properties of working like a random variable, it's going to finish.
Well, I guess there are two things you have to think about. One is the hash function generator, and the other is the hash function that was generated, right?
Right. The hash function that is generated doesn't have any pathologic cases. You saw the code.
Yeah.
So the question is for the generator, and actually the more interesting cases of needing more iterations are ironically the small key sizes. Because for small key sizes the chances of hitting the cyclic graphs are significantly larger than if you have a good tree size. And otherwise it really depends on what random hash functions you are using. If it's any good, it's going to work well.
So in practice, it's not likely that we run into that kind of problem.
Correct.
Yeah. Okay.
I mean, you could always use something like cryptographic hash function with some seeding, like an HMAC or so, but that's overkill, simply because they are going to be way too expensive to compute. What I want to look into is finding some very easy to compute hash functions, like the DJB hash, and see how well it can be used for small key sets. For example, Mandoc has a hash function for the different macros in it. So it would be nice to compute a perfect hash function for that, but it's very performance sensitive. So you want to have a hash function that is as cheap as possible, and that's one of the few areas where gperf might still work better if your keys are short enough and there are not that many keys. The computational overhead is significant, so finding cheaper hash functions would be useful. And I mean, if you try like 20-30 different hash families until you actually hit one that works, it's not a problem computationally. You don't even have to do that all the time, just whenever you actually change the key set. So, other questions? Well, thanks for your attention.
311.8 marker wrong?
No?
00?
/24.
Yes.
Yeah, okay.
So the last red marker should be 0, 0, right?
Yes. I'll fix that.
No, it's good. You tested whether I understood what you were talking about.
Yeah, exactly.
Yeah, thank you very much.